This is the Illinois 2399 bridge rail. It's mounted on the simulated bridge deck edge. It's also curb mounted. It can be used either for retrofit or for new construction. The first test is with an 1,800-pound car impacting at 60 miles an hour and 20 degrees. As you can see, the vehicle is smoothly redirected. The rails have a rather closed geometry, so the wheels and the bumper can't get in and snag on the posts. This is one of 6 bridge rails that we've tested and developed under an HPR pool fund study at Texas Transportation Institute. At present, 23 states and the District of Columbia are participating. This is a 5,400-pound pickup truck impacting at 60 miles an hour and 20 degrees. The third test was with an 18,000-pound truck impacting at 50 miles an hour, 15 degrees. We were a little concerned that the underside of this truck would snag on the top of the post, but as you can see, that didn't happen. The truck was smoothly redirected. This barrier was only slightly scuffed up after the test. It had plenty of reserve strength for heavier vehicles. That shows the vehicle after the test. It narrowly missed another bridge rail installation. This is a 32-inch high F-shaped bridge rail. It too is mounted on a simulated bridge deck edge. It's very similar to the New Jersey profile, except it's a better performer, as you can see in this test with an 1,800-pound car at 60 miles an hour and 20 degrees. It also works very well for pickup trucks, as you see in this test with a 5,400-pound pickup at 65 miles an hour and 20 degrees. The barrier was only slightly scuffed up during the test. The next test was with an 18,000-pound truck. 48 bales of hay were used to ballast it up to the test weight. These are the test vehicles required for Performance Level 2 in the new AASHTO guide specifications for bridge railings. As you can see, the vehicle was redirected and remained upright, but after the test we found out that the test impact speed was only 47 miles per hour. You'll notice that the bumper is not lifted up by the F shape, that it stays low, and the underside of the truck rests on top of the barrier. This limits the roll of the vehicle over the barrier, and as the vehicle slides along the top of the barrier, it helps keep the vehicle upright and redirected.
That's 32 inches?
That's a 32-inch high F-shaped barrier.
Okay.
This is a very, very slow film, and if you watch closely, you'll see the gas tank come off from the right. This points out that gas tanks are rather fragile and easily dislodged from vehicles, and that's something to be aware of in cleaning up after accidents. Here comes the gas tank from the right, and if you look closely, you'll see a bird flying in from the left. This was shot at 1,100 frames a second. We use high-speed film like this in order to get a look at what really goes on during a crash test. That mud, by the way, helped slow the vehicle down, but it didn't really affect the test results. Again, the barrier was only scuffed up, but was intact. So we told TTI to go back and rerun the test. They repaired the vehicle. The clearance from the ground to the underside of the truck is 39 inches. And it was deja vu. We got exactly the same result, and on analyzing the test results, we found out it was exactly the same test speed. They did it again at 47 miles per hour. So we had them rerun the test, and this time it hit at 52 miles per hour. And again, the result was the same. So you've seen 3 almost identical crash tests on the 32-inch high F-shape, and don't ever let anybody tell you that test results aren't repeatable. They are. The next barrier tested was a 42-inch high F-shaped bridge rail. The first test was with a 40,000-pound intercity bus. It impacted at 60 miles an hour and 15 degrees. As you can see, the vehicle rolled only slightly toward the barrier. The 42-inch height was sufficient to limit the roll of the vehicle. It was smoothly redirected and remained upright.
Why was the 42-inch height selected?
It was selected primarily for driver eye height considerations, so that people in full-size cars and small cars could still see over the barrier. But I'll show you another reason in a moment. The next test was with a 50,000-pound tractor trailer impacting at 50 miles an hour, 15 degrees. And in this test, the underside of the trailer came to rest on top of the barrier and slid along it. You notice also in this test there's no tendency for the F-shape to lift the bumper of the vehicle. And as you'll see later, that's important. The F-shape only lifts the vehicle enough to help reduce the friction between the tires and the roadway, and that aids in banking and redirecting the vehicle. As you can see from this overhead view, the tractor trailer is an articulated vehicle. The second impact, when the front of the trailer hits, is the critical impact. It produces the peak impact force. And you'll see how the vehicle is limited in rolling over the barrier. But of course, this has implications also for luminaire supports and other appurtenances placed on top of concrete safety shade barriers. We need to keep the tops clear. This is a 32-inch high vertical concrete wall. It, like all the other barriers, is reinforced with epoxy-coated reinforcing bars. The epoxy bars are made 15% longer, or J-hooks are used, in order to assure that we get the proper bond strength. You'll notice when this 1,800-pound car hit at 60 miles an hour and 20 degrees that the wheel was damaged, but not too severely, and the trajectory of the vehicle was good. However, when you have a rigid vertical faced barrier like this, damage to the wheel is sometimes unpredictable, and you may get high exit trajectories. So this is one trade-off with rigid vertical faced barriers.
Was that a dummy back there, or was it instrumented?
There was an instrumented dummy in the vehicle. This is a 5,400-pound pickup. Watch the wheel. The wheel in this case was critically damaged by hitting the vertical wall, but the test was still successful. This is a 42-inch high vertical faced barrier, and this is the 50,000-pound tractor trailer impacting at 50 miles an hour, 15 degrees. Even though the vehicle rolled over in the roadway, this is still a successful test because it contained the vehicle as required by the AASHTO guide specifications for bridge railings. It's not necessary to redirect it upright in order to be successful.
That was 32
What?
inches again?
That's 42 inches.
42 inches.
Watch
Okay.
the wheels of this vehicle, and you'll see that they're damaged so that the wheels are turned in to the barrier in a hard steer. And as the vehicle left the barrier, that hard left steer turned the cab, and that in turn pulled the trailer over. If this test barrier had been another 20 feet longer, the vehicle would have been redirected upright. So in some cases, we're testing vehicles, not barriers. And this is one reason why keeping the vehicle on the roadway is a success. The last test was with a 32-inch high New Jersey safety shape, a commonly used barrier. It had already passed tests with the 1,800-pound car and the 5,400-pound car. There's sound of a crash test on this section of videotape. You couldn't pay me enough to go near that burning vehicle. The New Jersey shape lifted the bumper of the vehicle up above the top of the safety shade. That allowed the top of the vehicle to knock the axle out, as you see here, and without the front axle and wheels, the vehicle could only overturn after it was redirected into the roadway. The New Jersey safety shape is still a perfectly acceptable barrier system, but the F shape exhibits superior safety performance. You can see here where the axle was knocked out in contacting the barrier. And you can see here where the wheel walked up the side of the barrier. The wheel just went right on up to the top. This is a glulam wood bridge rail. It's 32 inches high. It has a 12-inch wide curb, and the upper rail is 11 inches thick. So effectively, it's blocked out 11 inches or so to keep the bumper from snagging on the post. The first test was with an 1,800-pound car at 60 miles an hour and 20 degrees. As you can see, the vehicle was smoothly redirected. The wood laminated deck opened up right at the toe of the curb, so it would have to be beefed up in order to handle heavier vehicles. But that's easily fixed. This is a very aesthetically pleasing barrier. It has a rustic look, and a lot of states are interested in using it. It will also be used on many park roads by the Forest Service and other federal lands agencies. The Forest Service is currently developing a series of standard bridge decks, and they'll have at least 4 different bridge rail designs to go with them. The next test was with a 5,400-pound pickup truck at 60 miles an hour and 20 degrees. As you can see, the guardrail, or rather bridge rail, handled it easily.
What's this post spacing?
8'3" is the post spacing. You notice that the pickup truck flexes in the middle, and it acts a little like an articulated vehicle. So the impact force from this pickup truck is only about 45 kips. It's less than the old 4,500-pound car test at 60 miles an hour, 25 degrees, which produced a peak impact force of 56 to 59 kips. This is the Wyoming 2-rail bridge rail. It's another very aesthetically pleasing, very open design. You notice the bumper lines up exactly with the lower rail. This is an 1,800-pound car impacting at 60 miles an hour and 20 degrees. And the bridge rail worked in this test. The next test was with a Cadillac. And you'll notice that the bumper also lined up very, very nicely with the lower rail. This design is sort of fine-tuned to automobiles. But it's been used by Wyoming for a long time and been an excellent performer. As you can see, it's only scuffed up a little in this test. This is Missouri's new Thrie-beam bridge rail. It has a steel channel on top of the post, and again it was mounted on a simulated bridge deck edge. The first test was with an 1,800-pound car at 60 miles an hour, 20 degrees. You notice the dummy's head went through the window. It takes very, very little to break that window. That's not a serious or fatal injury.
The dummy wasn't in a seatbelt?
The dummy was in a seatbelt, but the seatbelt broke loose during the impact, which is rather rare.
Okay.
This is a 4,500-pound car impacting at 60 miles an hour, 25 degrees. You'll notice the hood became unlatched in this test because the front grille structures of these vehicles are rather weak. It's not at all uncommon for the hood to pop open. But this doesn't negate the test. It was a successful test. The barrier, however, needs a little bit of improvement. We saw some shearing of the Thrie-beam rail at the edge of the steel post, and a backup plate needs to be put there in order to handle heavier vehicles. Also, there was some distress of the deck, some cracking, and a few more rebar should be put in there. This is an Iowa retrofit design. It's a concrete block mounted on a curb in order to upgrade an old bridge rail. As you can see, the car scraped along it and came to a safe stop. This is a popular type of retrofit design because it saves a lot of labor in removing the old curb. It's also been tested with a 5,400-pound pickup at 60 miles an hour and 20 degrees. This is an older Iowa design, an aluminum bridge rail mounted on a curb. And as you can see, the aluminum rail deflected too much, and that allowed the car to climb up on the curb with disastrous results. This shows where the wheel climbed up on the curb. We've known for a long time that old concrete baluster rails have insufficient strength. California ran this test almost 2 decades ago.
Still a lot of those out on the highway, though.
There are about 1,100 miles of concrete baluster rail still in service throughout the country. Washington has come up with a solution. This is a 10-gauge Thrie-beam rail that's bolted to wood blockouts, and then the bolts go through holes drilled in the vertical pilasters behind. The blockouts are spaced approximately 6'3" on centers. Each blockout is made of 2 8x8 wood posts, but deeper blockouts could be used. The first test was with an 1,800-pound car at 60 miles an hour and 20 degrees. The key here is that the 10-gauge Thrie-beam works in cooperation with that curb to make a rigid barrier. It's not at all unusual for the hoods of these small cars to come loose like that, as you see. The next test was with a 4,500-pound car at 60 miles an hour, but an impact angle of only 15 degrees, because the state highway officials wanted to see what would happen in a more typical accident. The brakes failed in this test, and as a result the vehicle went careening off the road, but this is what would happen if the driver wasn't able to apply the brakes in a real-world accident. And that's something to keep in mind. Crash tests are staged accidents. We're trying to find out how the hardware performs under dynamic load. And sometimes we get surprised. You'll see the 5,400-pound pickup just barely missed that tree after this test. The sheet metal was wrinkled up and, of course, would be replaced for aesthetic reasons, but it's still serviceable. The concrete baluster rail had some hairline cracks. You can see them marked here by the little black arrows. And there was some spalling of the concrete at the bottom of the post. You'll see the spalling as the camera pans down to it. Here we are. But that's very good because the calculated strength of this rail is only 3 kips. We then developed a transition to it. The transition was extremely stiff in order to keep the wheels of vehicles from snagging on the end of the sidewalk at the bridge end. There are other ways of addressing this. We could have cut a bevel out of the end of the sidewalk there, or added a wedge of concrete to help redirect the vehicle. But those things would have caused corrosion problems or interfered with drainage, and as a result we elected to go with a very stiff transition. This was an attempt by Texas to develop a wood post guardrail that could be used on low-fill culverts. However, instead of having the customary 38-inch embedment depth, the posts were only embedded 18 inches. And as a result, the posts had insufficient foundation strength. They leaned over and formed a ramp that launched the car right over the barrier. This can happen also with regular guardrails, and this is why FHWA has advised leaving washers off of guardrails so that when the posts lean over, they won't drag the rail down with it. Texas went to steel posts that were bolted to the top of the concrete box culvert. And this restored the strength of each post and made it a very serviceable guardrail, as you see in this test with a 4,500-pound car at 60 miles an hour, 25 degrees. There's a lot of interest on the part of the states in developing guardrails on low-fill culverts that don't have to be attached to the box culvert. They don't want the box culvert damaged. The state of Washington is sponsoring tests to look at 1 or 2 short posts in combination with nested W-beam, and the state of Ohio is sponsoring tests where it would be backed up with structural steel tubes. We've run a series of pendulum tests on guardrail posts, in order to look at their force deflection characteristics. We've found that when guardrail posts are set at the slope break point, that the lack of foundation behind the post greatly reduces the post strength. However, making the post longer, about 7 feet long, restores that strength. So it's possible to relocate the post back at the slope break point and thus gain more shoulder for the roadway. However, the posts have to be longer, and there's a maintenance consideration. You have to make sure that the maintenance man doesn't come back after an accident and replace it with a short post. This is the stone masonry guard wall used on the Shenandoah Parkway. It has a inverted concrete T core section, and then the front is infill with decorative stone masonry. This test is with a 4,500-pound car at 60 miles an hour, 25 degrees. As you can see, the car was redirected upright. In an earlier test, the core was only 18 inches above grade, and as a result, we knocked 20 feet of stone off the top of the barrier because the impact force didn't go directly into the concrete core. It was shearing the rocks off the top of the core. So we recommend a minimum core height of 20 inches. This is much less expensive than trying to build an all-stone wall, and because of that reinforced concrete spine, it has the structural strength needed to be a positive barrier. It's a very aesthetically pleasing barrier. You'll see where a few stones were chipped off the front face of it, but that could easily be repaired. This is an artificial stone masonry guard wall. That's a 3.5-inch high Washington, D.C. standard mountable curb in front of it. It's placed 12 feet in front of the barrier, and there's a 2% slope up to the barrier. You'll notice the shiplap joint at the end of this barrier. This barrier really consists of a series of 10-foot-long precast concrete sections. The stone faces are molded in latex molds, and each stone is stained to look exactly like natural stone. Each of the 10-foot-long units weighs 12,000 pounds, and that's a disadvantage because you can only get about 4 of these units on a truck. The first test was with a 4,500-pound car impacting at 60 miles an hour, 25 degrees. And I think you'll agree that looks like stone. The top looks exactly like natural granite. There are lifting lugs provided in the back of the barrier to help install it in place. In this impact, the barrier deflected backward about 2 inches. Those joints are designed to swivel in order to accommodate horizontal alignments in the field. And as a result, there is some flexibility in this barrier.
How rough a stone is too rough?
Well, we found that you can have mortar joints recessed up to 1.5 inches, and you don't want any jagged points or obvious snag points. But if the barrier is made with reasonable care, it will be a good performer.
What angle was that?
That was at 25 degrees. The face of the barrier was scuffed up a little bit, but that could easily be restored using some muriatic acid.
Is this the one they're planning to use at the BW Park?
They're planning to use this on the Baltimore-Washington Parkway. The first project has been awarded. They project it will save $8.8 million over the entire length of the project. This is a low-speed steel-back timber guardrail. It's used in cases where impact speeds of 50 miles an hour or less would be expected, and that's true of most park roads. The posts are spaced 10 feet on centers. There's a single bolt connection from the rail to the post, and the washer is recessed in the back both for strength and aesthetic considerations. As you can see in this test with a 4,500-pound car at 50 miles an hour, 25 degrees, it behaves like a stiff, rigid barrier system, but it's a very good performer. The high-speed timber guardrail is the same design, except it incorporates a 4-inch deep blockout. We've standardized the rail hardware for the sake of economy and for simplification and maintenance. We don't have a crash-worthy end treatment for that, so it has to be either buried in a fill slope, as you see here, or an earth mound placed on the end of it. This is a typical state buried in back slope design for a W-beam end. This impact is with a 4,500 pound car at 60 miles an hour, 25 degrees. The terrain in front of the barrier slopes down to the barrier, and as a result the car became airborne and hit the barrier higher than you would have expected. But it's a simple ballistics problem. The car fell on the W-beam and sheared it, and then it went on to roll over, as you see here. Now, I'm sure all of you knows a friend who knows a friend who has been in a rollover accident and has lived to tell about it. But I can assure you that a rollover is a very, very severe event. As long as the occupant's head and arms stay inside the vehicle, they have a fairly good chance of getting out of it alive. But if they're ejected from the vehicle, usually it's a fatality.
What was the problem there? You had the rail was coming down following the ditch slope.
The problem was that the rail height was with respect to the elevation at the bottom of the ditch, if you will. The terrain sloped down to the barrier, as you see in this view. And because the car was traveling at high speed, 60 miles an hour, it simply didn't fall fast enough to follow the sloping terrain as it sloped down to the barrier. So, of course, the fix for this was simple: to raise the barrier and to put a W-beam rub rail underneath. And I think you'll agree that that's a great improvement in performance. There are many, many states that are using designs like the one I showed you earlier, and this is something that needs attention. This shows the barrier after that strength test. We also ran a test with an 1,800 pound car at 60 miles an hour and 20 degrees in order to make sure the rub rail performed as intended. And as you can see, that end treatment also worked very well in that test. This shows the barrier after the test. Not too much damage. We've been developing a Thrie-beam bullnose for wide medians. This shows one of the earlier developmental tests. As you can see, it wasn't successful. The Thrie-beam wrapped around the car as intended, but then the Thrie-beam slid up and impacted the windshield. And that doesn't just mean that the occupants get acne from the broken glass. That would mean a fatal slap in the face. So we went back to the drawing board and came up with a new design. The new design uses a flat plate element on the nose, and there's a groove on the bottom in order to interface with the bumper of the vehicle. The side guardrails are modified Thrie-beam guardrails, which is about the safest guardrail we have today and gives you the best bang for the buck. This new bullnose worked very, very well in this test. You'll see where the windshield popped out of the car in a minute.
Well, the car had to hit it right in the center.
No, we've run a whole series of tests with pickup trucks hitting from the side, and we need about 6 more development tests in order to satisfy ourselves that it performs as intended in the design. And this is what I'm trying to give you a flavor for. Very frequently we only show you our successful tests, and we don't show you the development tests that led up to it. But in some cases where the hardware is fairly complicated, or where you have large elastic plastic deformations, it's necessary to run a whole series of tests in order to come up with a successful design. This is an instrumented wall at TTI. Each of these panels is backed up by load cells at the corners. We're measuring the impact forces from vehicles such as this 80,000 pound gasoline tanker, which impacted at 50 miles an hour, 15 degrees. You notice the gas tank came off again. We've also been running tests with articulated tractor trailers, as you see here, and you'll notice it flex in this overhead view. We're taking this test data and extrapolating it downward in order to develop design forces for lower height barriers. This one's 90 inches high. We're also going to try to come up with design guidelines for designing bridge rail to deck connections. This is a quad beam median barrier. We were looking at the feasibility of developing soil-mounted median barrier systems for performance level 3 and performance level 2 when the test requirements in the AASHTO guide specifications for bridge railings would be applied to guardrails and median barriers. That's sometime in the future. This 50,000-pound tractor trailer impacted the quad beam barrier at 50 miles an hour, 15 degrees, but the barrier came unzipped, if you will. The posts were pushed down by the impact. The rails came off of the blockouts, and when the weight of the trailer fell on top of the barrier, it simply flattened out and unzipped. You'll notice up on the back of the truck there are a whole series of umbilical cords. Those cables are used to collect the data. It's being recorded remotely about 300 feet behind this barrier. So we still have a lot more homework to do in order to develop a soil-mounted median barrier that can handle a performance level 3 type tractor trailer test. But we have one for performance level 2. This is a median version of the modified Thrie-beam guardrail. It uses the same blockouts, the same posts, the same hardware. It's simply a double barrier. That cutout in the blockout keeps the rail face vertical on impact, and that greatly helps automobiles and in tests like this with a heavier vehicle. As you can see, the 18,000-pound truck was very smoothly redirected in this test.
Is that fully loaded, sir?
Yes, it was ballasted up to 18,000 pounds, again with bales of hay. The barrier was only scuffed up a little. And, yes. A question?
What is the cost of the barrier like that compared to just using a concrete shape as a median barrier? I can see someone saying this is going to be a headache.
I would say it would be about $30 a foot. This is South Dakota's new 3-cable guardrail. The posts are made of re-rolled rail steel, and as a result they cost $1 a foot less, or about 10% less. So there's a great saving in cost, but it's also a good performer. The upper cable has been lowered to 27 inches so that it doesn't slide up and over the roof of cars. And a transition has also been developed from this 3-cable guardrail to a W-beam. This test is with a New Jersey safety shape that has been lifted up 1.5 inches and placed on a 1.5 inch grout pad. The 1,800-pound car hit at 60 miles an hour and 20 degrees, and it was lifted up too high on the traffic side of the barrier, and as a result the vehicle became unstable. A test was run last week with another car, a Volkswagen Rabbit, under the same test conditions but with no dummy, and the vehicle was right on the ragged edge of rolling over, but it remained upright. But it's clear that if you raise the slope break point of the barrier above 13 inches, you greatly increase the potential for small cars to roll over. So the slope break point should be kept to 13 inches or less. The F shape has a slope break point of only 10 inches, and that helps solve the problem. But occasionally, slip forming machines ride up and produce a slope break point that's too high, or contractors don't make the concrete safety shape properly, and this is something to be sensitive to when you're in the field. Energy absorption systems ran the next 2 tests in order to demonstrate the need for impact attenuators, but this also shows that it's important to have a good guardrail bridge rail transition at a bridge end, that bridge ends are serious fixed obstacle hazards. This concrete safety shape end penetrated 4.8 feet into the vehicle, and the motor block wound up back in the driver's lap. That was at 58 miles per hour with that little 1,800-pound car. In the next test, they turned down the end of the safety shape at 22 degrees, And then they ran a test with a 4,500-pound car impacting head-on at 63 miles per hour. But I think you'll agree that that's not a solution to the problem. The car was launched 150 feet into the air. It landed on its side and slid another 50 feet. And that's a very, very severe accident. So we need good guardrail bridge rail transitions. Until a few years ago, this was considered a state-of-the-art guardrail bridge rail transition design. It had a 37.5-foot long breakaway cable terminal. The post spacing was reduced from 6'3" to 3'1½", and the W-beam was rigidly attached to the bridge end. However, even these modifications didn't produce a crash-worthy design. When this 4,500-pound car impacted at 60 miles an hour and 25 degrees, the guardrail deflected in too much in the transition zone. That allowed the car to push the concrete block forward, and that tore the W-beam rail. This impact was so severe that we actually had to cut the dummy out of the car. We've never had to do that before. This is a transition test conducted under NCHRP Project 22-4, Performance of Longitudinal Median Barriers. The test was on a New York transition, and as you can see, the front wheel snagged on the first bridge rail post. While traditionally we've tested transitions only with the big 4,500-pound cars, in designing transitions we need to be aware that they have to perform adequately for small cars as well. And in order to eliminate snagging problems like this, we have to consider that in design. So when we came up with a fix for the transition design I showed you before, we added this W-beam rub rail. We nested another W-beam over the top W-beam, and then to further increase things, we added 2 posts to make the spacing of the first 4 posts 1'6", as you see here. And those design changes greatly improved the performance of the system. The car was smoothly redirected. There wasn't much deflection of the barrier afterward. You can see that's a big improvement. This is an 8.5-foot radius curved guardrail, and the first test was of the original design. This was a developmental test. There were 4x6 wood posts placed in the nose so that they would break away on impact, but they didn't break away. They leaned over and formed a ramp that helped launch the car right up and over the transition to the bridge end. There was also a steel cable there that was intended to help bring the tension force in the W-beam around the curved section, but subsequent research showed that that wasn't necessary, that as long as the W-beam was wrapped around the end like that, it would perform adequately. So we modified the posts. We used CRT posts. These 6x8 posts have a 3.5-inch diameter hole drilled at ground line and another one 16 inches below grade. This first test was with an 1,800-pound car at 60 miles an hour, 20 degrees. I misspoke, 60 miles an hour, right on the nose of the barrier. There's a 2-to-1 slope behind the barrier, and the posts are set back 2 feet from the slope break point. So this is very typical terrain. We could have tested it on flat and level terrain, and it would have worked even better, but we don't believe in kidding ourselves. We want to know how the hardware will perform under actual field conditions. This is admittedly a severe test, but it shows you that this breakaway curved guardrail can contain even a little 1,800-pound car. The next test was with a 4,500-pound car hitting right on the nose at 60 miles an hour. We left the transition alone for this test. The same breakaway posts were used. However, there was a bolt on the center post in order to help support the rail. That bolt tore the rail and allowed the car to penetrate. We made a number of design changes. We added a driven steel foundation at the second post. We connected a cable to that. We added a pivoting pipe support to the end post so the W-beam would rotate and follow the car. We bolted that second cable to the first cable and then to the end anchorage. That made sure the cables remained attached to the W-beam and still allowed the W-beam to develop tension in the rail. This time out, however, we removed that bolt from the corner post. The washers were removed from the adjacent post in order to help the rail separate from the post. And I think you'll agree that that was a whole lot better. It contained the vehicle. It kept it from getting back into the hazard. We then reran the first test that launched the car to see if those CRT posts provided better performance, and they did, as you can see here. But we still hadn't gone back and tested the transition itself. And the transition was a rather simple one. We had just reduced the post spacing to make the first 4 posts spaced at 1'6", and we had only one W-beam rail connected to the concrete safety shape bridge end. As you can see in this test, that didn't provide adequate strength or stiffness when a car hit it at 60 miles an hour, 25 degrees. The guardrail deflected in 42 inches, and that allowed the car to strike the end of the safety shape. It struck it so violently that the safety shape itself was snapped off several feet back from the end, as you'll see in this next view. So simply reducing the post spacing isn't enough to stiffen up a transition enough to make it work. You have to put more metal in the rail. One thing that will help, though, is to make those posts longer in the transition design. That does help stiffen up the transition, and it's also very beneficial where you might expect erosion right behind the transition. This shows the damage to the concrete safety shape. It snapped off, as you see here. We then began to develop a good direct transition from the approach W-beam guardrail to the safety shape bridge end. It had a nested W-beam over the top W-beam. It had a cold-formed rub rail connected to the concrete safety shape by means of a special end shoe fabricated from a 6-inch hot roll channel. That rub rail has as much steel in it as a W-beam, so it's a very strong, stiff flexural member. And then we ran a test again. You notice there was a wood block out between the end of the safety shape and the W-beam. That was intended to soften the blow a little bit here. But it turned out that the wood block out was a hard spot, as you can see in this overhead view. This was still a big improvement over the earlier test, but we made one more design change in order to further improve its performance. You notice how the hood went over the top of the safety shape. I'll talk more about that later. We have observed hood snagging problems where posts extend upward above 33 inches. See there where the wood block out made a hard spot at the end of the bridge rail. So we used exactly the same details. The rub rail tucked behind the post, the same post spacing, but this time we had a collapsible pipe block out. It was 6 inches in diameter and 9 inches long, and it's bolted only to the back of the W-beam. We tested it on a 35-foot radius curved guardrail that we've been using for other tests. And the tests on the 35-foot radius curved guardrail showed that when a 4,500-pound car hit the nose at 60 miles an hour, the W-beam had to deflect backwards so far before it would start to develop tension with a 35-foot radius that it was a very marginal design. So this is only recommended for 50-mile-an-hour impact conditions. 35 foot is the biggest radius you should use. This test was on the transition, and as you can see, the new direct transition was very successful. That cameraman had to run for his life. But that points out another aspect of safety. We have to be very careful when we run crash tests to provide safety for the crash test crew.
You said 35-foot radius. You meant sharpest radius. Is that what you meant?
No, we've tested 8.5 and 35-foot radii curved guardrails, but I wouldn't use a 50-foot radius curved guardrail, for example. This is a steel post direct transition. It's basically the same design as the wood post design you just saw, but these direct transitions offer an advantage. they don't require 8 or 9 feet of vertical concrete wall before getting to the bridge end. You notice the hood popped up here, and we were a little concerned that the hood might have snagged on the top end of the concrete safety shape, but as you can see, it didn't happen. It went over it. But we recommend for new construction that the end of the concrete safety shape be beveled in order to minimize the potential for hood snagging. We're going to be testing another type of direct transition soon for Missouri. This is a Montana design. It uses a 7-foot long section of tapered precast concrete curb to push the wheel out and away so it won't snag on the end of the concrete safety shape as you see here. This test is with a 4,500-pound car at 60 miles an hour, 25 degrees. And you'll notice the car almost missed 2 trees downstream. And this points out the importance of the clear zone concept. We've done nothing if we have a good bridge rail or a good guardrail or a good transition, only to have the car and the car's occupants killed 50 milliseconds later when they hit a tree. This is a stiff-legged sign support system used by Wisconsin. The first test was at 20 miles an hour. We reused the sign panel and the hardware. In this design, there's no upper hinge under the sign panel. The breakaway mechanism is the steel clips that connect the sign panel to the stiff leg. And as you can see in this 60 mile an hour impact, the clips tear away very readily. It's a very good performer. There have been 2 sizes tested to date. The old upper hinge necessitated having a 4-bolt slip base, a directional slip base at the bottom so that the hinge would activate properly. But this type of design lends itself to having a triangular slip base at the bottom so that it will perform well even in side impacts. And I'm hoping that someone will take the next step and develop a triangular slip base design. We've been running side impact tests at our foil test facility in McLean, Virginia. This is a 1,800-pound car, and it's going to slide sideways into the pole at 30 miles per hour. Now, the deck has been stacked in this test. As you can see on that door line, the pole will contact the shoulder of the driver, and his head hit the pole. A head injury criteria number, or a HIC number, of 1,000 indicates a fatality. In this test, the HIC number was 9,000. So you could say we killed him 9 times over. But we're running tests to see how sensitive this is. What would happen if the pole impacted 6 inches in front of the dummy, or 6 inches behind the dummy? Now, it's just how critical is the side impact situation, and what can be done from a hardware point of view. From a vehicle point of view, the solution is easy. Drive a big car. This big old 4,500-pound Chrysler worked beautifully in this test. There was very little penetration of the side sill, and the dummy's head saw a HIC number of only 100, not even enough to call for an aspirin. You'll notice the spectators up on Observatory Hill. We're safety conscious at our test facility as well. We've also been running a series of tests on the currently acceptable luminaire supports. This was an early development test, and in this test, the transformer base broke away. However, in the compliance test, none of the aluminum transformer bases broke away. This is a New Jersey breakaway barricade, and you'll notice that the panel on this Type 3 barricade is up fairly high. That provided good behavior because the sign panel was able to get up and over the roof of this vehicle. You'll see it here as it sails up and over the roof without impacting the windshield. I point this out to you because even seemingly insignificant details become crucially important when you're dealing with dynamic loads. This earlier development test, where the sign panel was mounted down low, was not successful. It's also crucially important to keep the ballast down as low as possible. You'll see in that test the sign panel hit the windshield and dished it in. And that can be a very severe impact. This next view shows the dished in windshield. The The plastic parts are scattered over a wide area, as you would expect. And here's the dished-in windshield. So you really wouldn't want to be sitting in the front of that car. This is a test New York recently ran on another breakaway barricade. It was impacted at 60 miles an hour. And notice the debris spray downstream. Workmen need to be cognizant of this, and some guidelines really need to be developed on how close breakaway hardware like this can be placed to men working in construction zones. New York ran an extensive series of tests on channelizing devices with lights and batteries on top. And I'm going to show you one of the more dramatic tests. They placed a cinder block on top of a channelizing device, and then a car impacted it at 60 miles an hour head-on. The cinder block predictably flew back through the windshield, but it hit so violently it pushed the hatchback out in the rear, as you see in this view. Anyone being hit by that flying cinder block would have been a fatality, I'm sure. Even the batteries of the lights could be hazardous, and New York is recommending that the batteries be placed low and connected to the light by a wire. This is a breakaway mailbox design developed by Nebraska. This is the single post design. And as you can see in this 60 mile an hour test, it's a good performer. Yay! The state ran tests in both weak soil and strong soil. This is a double box design. These are hat section posts of the kind used to support stop signs. They tend to have a lot of audience participation in that state. As you can see, the mailbox design was mowed down as intended. The breakaway connection performed as designed. We've known for a long time that high curbs can launch cars. This old bridge rail test shows it very dramatically. The car snagged on the concrete bridge end. And we're looking at guardrail curb combinations. We've never run tests of guardrails under curbs. This is a 6-inch high asphalt curb, and the steel posts are driven into the asphalt. The first test was with an 1,800-pound car at 60 miles an hour and 20 degrees. As you can see, the car was very smoothly redirected. It was redirected parallel to the barrier, which is exactly what you want it to do. The 1,800-pound car just didn't have enough weight, enough punch, to push the guardrail back from the curb. The next test was with a 4,500-pound car impacting at 60 miles an hour at 25 degrees, the old classic strength test for guardrails. And this car did have the punch to push the guardrail back. Typically, a guardrail deflects back 33 or 35 inches under this impact. That allowed the wheel to get in contact with the curb, and the car took a dynamic jump and got up on top of the guardrail. You can see the car climbing on top of the guardrail in this view. The car rode along the guardrail for 100 feet or so, and then it fell back off on the traffic side. We're going to use these tests to validate a computer simulation program, and then we're going to make parametric studies to see how high the curb can be before this sort of thing occurs. Perhaps a 4-inch curb would be adequate, but at this time we just don't know. That puff of smoke was the wheel blowing as it contacted the steel post. But this shows that with a 6-inch curb, the guardrail is right at its performance limit. We also ran a test with a 8-inch high concrete curb. It's the Type A curb shown in the old AASHTO barrier guide. And that's the next test I'll show you. This is the curb and gutter combination. The curb, again, is tucked in under the face of the W-beam rail. You'll notice in this view that the bumper of the pickup truck is higher than the bumper of the car. So the deck is already stacked a little bit against this guardrail. When the bumper pushed the guardrail back, the wheel came in contact with the 8-inch curb, and that produced a dynamic jump right over the guardrail. The pickup truck landed 75 feet away and about 15 feet back from the barrier. So we obviously need to come up with some improved design guidelines for guardrail curb combinations.